Hi, physical students. Today is an introduction, or the purpose of this video is to introduce week 14. This is the week before Thanksgiving. We have an interesting chapter, chapter 13, which is part of the exam. As you see, in this week, we have an exam review. We have exam 3 review. And exam 3 includes chapters 9, 10, 11, 12, and 13. So it's important that we prepare for the exam. Let me share with you the objectives for the week. We have a review, excuse me, that is due on Monday, November 29th, because the exam is going to be on November 30th, the day after, and that is after Thanksgiving, of course. We have still lingering discussions from the previous weeks, and they are due on this Saturday, actually the 20th. So it's important that you guys submit them. We also have a discussion that is due after Thanksgiving, and that is Saturday, December 4th. The chapter deals with the atomic nucleus, or the nucleus, and the radioactivity. And I'm going to go briefly on this ideas. And this does not replace the fact that you have to read the chapter and do complete all the activities related to it. That is how you're assessed, whether on homework assignments or quizzes or exams. There is also an online survey that is still there. Please complete it so that we basically assess where the course is and how we can move on to make sure that this course benefits. If not immediately, I'm hoping immediately, you guys, at least the next group of students. These are the objectives of this chapter. So let me delve into the content a little bit. The topic for this chapter is the nucleus of the atom and radioactivity. Chemistry really deals with the electronic, or the electron itself in the shell, and how it interacts and how it bonds and so on and so forth. But sometimes it helps to understand what's going on if we dive in a little bit inside the nucleus or inside the atom and see exactly what's going on in it. Radioactivity is an old phenomenon. One of the at least misconceptions that is out there, it's as if it's somehow related to the industrial activity of modern, basically, society, and that is not true. Radioactivity existed for a long time, and it powers one of the most powerful things on Earth, which is the heat that is generated inside the Earth, and which is responsible for the magnetic field, really, of the Earth, and that is where radioactivity comes in. It's also responsible for what's going on in the stars. It is the trigger point for the nuclear reactions that happen in the star. Without radioactivity, there could not be any light from the stars. There could not be any, basically, magnetic field of the Earth. A lot of the things don't happen. So this is an old concept. When we tested it initially toward the beginning of the 20th century, it turns out it comes in 3 types. There is the so-called alpha particles, and alpha particles, basically that's how I think they were classified by Rutherford. Alpha particles, beta particles, and then you have the gamma particles. Turns out the alpha particles are nothing but the nucleus of the helium atom. You have 2 protons and 2 neutrons. And then the beta particles are nothing but an electron. The gamma particles turn out to be gamma rays, and you can see that the alpha particles are charged particles, whereas the beta particles are also negatively charged, and then the gamma rays do not have a charge. Furthermore, if you put them in a magnetic field, remember the magnetic field has an effect on a charge using the right-hand rule, and it's going to bend it depending on the sign of its charge, one way or the other. So if you have a source of radioactivity in here, and the particles are coming straight out, shooting out of the source, and you put them inside a magnetic field, depending on their charge, they will bend one way or the other. If they don't have a charge, they will not bend, they will go straight out. And that's where the gamma particles come into play. Also notice the bending in here, or the curvature of the bending is a lot sharper in the case of beta particles, whereas it's less, the radius of curvature is actually much bigger in this case for the alpha particles than that of the radius of curvature, which is sharp angle, which is a lot less radius. So it curves a lot in this case. It bends very quickly for the beta particles. And that has to do with the mass, actually, because of the law of inertia. This one has a lot more mass. It's about 8 times more than this one. And 8,000 times more will make it so that it bends less versus that of the beta particles. Anyway, this is a natural process, and it's due to the so-called weak force. Just a reminder, there are 4 forces in nature. The gravity, force of gravity, and that's a super weak force. We never talk about it when it comes to these processes because it's practically 0, 10 to the negative 40 compared to the electrostatic force, which is the next force that we know of. The electrostatic force is responsible for electricity and magnetism. That powers most of our modern technology. And then you have the nuclear forces, which are 2 of them. One of them is the weak force because it requires short-range interactions, extremely short-range interactions for it to happen, and that is radioactivity. This is the one we're talking about. Then there is also nuclear force, the other one, which is a strong nuclear force, which is the strongest force ever in terms of intensity, okay? So those are the 4 forces. Radioactivity is coming from the weak force, the weak nuclear force. And that is basically what's going on in here. As all of the atomic forces, atomic phenomenon, it's probabilistic basically, but that's how the electron even itself exhibits itself in the outer shells too, using the hypothesis of quantum mechanics. Radioactivity, or at least nuclear transformations, they can occur in one of 2 forms, either naturally or artificially. Naturally, like, for example, the decay of any material, okay? Most of the materials are radioactive anyway. Like what happened also inside the cores of the stars. Like what happened, that is during its main life, basically, for the star, or during its cataclysmic event, like, for example, supernova or something like this. So that is natural processes. Or artificially, like the ones we produce either in the lab or in some sort of a military applications like bombs. So this is basically how nuclear transformation happen. And when they do, they deliver a tremendous amount of energy because of this expression, because of the mass energy equivalence. Remember, C is just a constant. That's the speed of light. Squared, it's still a constant. So it's 3 times 10 to the power 8 squared, which makes it 9 times 10 to the power 16, which is still just a number. But it's a big number. That means it takes just a tiny amount of mass to transform. And when you multiply it by a big number, it's going to be a big energy. So that is basically what this expression is. So during a process where there is an exchange of energy, a drop in mass, there is a release of energy that is equivalent to this expression. The drop in mass in here, delta M times C squared, that's how much energy is released. But if the nuclear reaction is endothermic, meaning it requires energy, then you need to increase the mass by this amount. And that is, you have to multiply it by C squared to get how much energy is needed for that nuclear reaction to happen. By the way, and I probably should not say that, but the beta decay, for example, or the alpha decay usually requires a lot of energy during the instant itself. And we're getting into a little bit of nuclear physics, but the point being in here, there is an exchange of the W plus or the W minus or the Z bosons, and those particles are extremely heavy in mass and require a lot of energy. But how can we explain it, especially when it comes to neutrinos, which part of the products that are involved usually with this kind of reactions? And the explanation for it has to do with something in physics called the Heisenberg Principle. Okay, because on a very short time, you can borrow as much energy as needed, and the mass in that case can be very heavy, and the energy can still be very big at that point, but it's for an extremely short period of time. Anyway, so this is basically the idea behind radioactivity. Radioactivity, one of its applications in radiometric dating. And radiometric dating is basically if you know the lifetime of a sample, carbon-14, for example, how long does it take for carbon-14 or half of the carbon-14, no matter how much you start with, to go into carbon-12? Then in this case, you can use that to date whatever organic material, or at least what was organic material before it died. That is one thing, one of its applications in carbon dating, or it could be used also in geology for bigger time spans, when you know that the half-life is in millions or billions of years, then you can tell the age of a sample depending on the ratio of the daughter versus that of the parent. We call them, that's how they are. Basically, in this scenario in here, the parent is uranium-238, and the daughter in this case is thorium-234. Okay, and the production in here in this case is helium. Albeit this process is actually yeah, this is a natural process. This is not an artificial process, and the lifetime can be very, very long in this case. Anyway, half-lifetime, that's basically one of the things that we should be talking about in here. One of the things to pay attention to is what happened to the atomic mass and the atomic number during a decay, which is really telltale sign in here. For example, uranium-238, we had 238 nucleons, we dropped by 4 because we released, remember, an alpha particle. An alpha particle has 2 protons and 2 neutrons. So in this case, we dropped from 238 down to 234. That means the number of neutrons dropped from 146 to 144 because we lost 2 of them to make up the helium. And then we also lost 2 protons because we had 92 and we dropped to 90. So we moved in the periodic table during this process. The same thing is happening also with the beta decay. The beta decay also will require a change in the, in this case, the atomic number, because you have a somehow the production in this case, the nuclear reaction typically for the beta decay in this case is the neutron will transform into a proton plus an electron. So the electron is what you measure from it, and the proton, actually the number of proton will increase in that nucleus, and that's basically what's going on. In the case of the gamma decay, there is no change in either. The atomic number and the atomic mass do not change. You don't migrate on the periodic table, you stay where you are, okay? But the atom goes down from an excited state, or the nucleus goes on from an excited state down to a lower state. Okay, so this is enough about this idea, but hopefully you guys can read through this and ready yourselves for the exams when it comes to these questions. One of the important things, of course, one of its applications for this one is the artificial nuclear transformations, like, for example, the fission. You hit uranium-235 because it's very unstable. You hit it with a neutron, fast-moving neutron. In this case, you produce, among other things, a krypton and barium. But you will have 3 neutrons, and plus, of course, release of energy. That's really what you want from nuclear fission. You take that, and if you don't control, the chain reaction can be out of control. And if you have a critical mass, that thing can basically result in explosion, result in an atomic bomb. Same thing with the fusion also, you can do a similar phenomenon. With the fusion, you have the nuclear reaction basically starts and can be, if it's not controlled, can also result in a big explosion too, and that is the hydrogen bomb, for example. Anyway, the point that I want you to remember from this one also is this curve. It's a very important curve, and it tells you the mass per nucleon, how much mass can be basically released if we go through the curve in here for the based on the atomic number. In this side in here, you have fusion. you take lighter elements and you fuse them and you make heavier and heavier elements. As the atomic number increases, you're producing from hydrogen, producing heavier and heavier elements. And here you start from heavier elements and you go through the curve backward in this case, in such a way that the atomic number decreases. So you have fission really on this side and you have fusion on this side. Up to iron on either side. Iron is basically the lowest mass per nucleon you can have. So that's why in the core of stars, star can make, if it's heavy enough, can still make elements, heavier and heavier elements using fusion in its core and produce more and more energy and basically balance itself with the gravity against the force of gravity by producing enough pressure and stays more or less active. The minute it produces iron, the nuclear reactions that can happen potentially after that, they don't produce energy. So the star will continue collapsing until it explodes, provided the star is heavy enough, as I was saying, into a supernova. Supernovae, the phenomenon itself, has high enough energy to produce the heavier elements. And that's how the other elements past iron are produced. And if the star is small enough, that will not happen because you cannot reach the iron. You're going to produce probably carbon and oxygen, and the star basically will run out of energy at that time, run out of fuel at that time to produce more and more elements, and basically end up in a white dwarf. This explains a lot for us because we usually basically state that once a star produces iron, the star has reached basically has signed its death certificate, if you wish, okay? Because it's going to collapse immediately after that. There is not enough energy produced to balance the gravity, the force of gravity. But for our applications, this is one of the things, at least for physics in here in this class, is one of its applications. Of course, understanding what's going on in stars is important. Actually, it's one of the objectives for this one, okay? For this class. But the point also is this is what is used in nuclear fission, which is mainly powers our nuclear reactors. And one of its applications in the military is, like I said, the atomic bombs. And this is what potentially still in the research, not controlled, yes, is also going to be useful to produce energy in the case of the nuclear reactors using fusion, but it's still in research stage at this point in the year. But it has the potential to produce far more energy if it's controlled. If not, it's really a hydrogen bomb in this case. I did not really mean to go into a lot of details in this introduction. I hope you do the reading because it's required, number one, and it helps you prepare for the exams and the assignments. Do not forget to do the review. Thank you.